Hello, and welcome to the course. I'm Stephen, your host for today, and I'll be speaking with Professor Joshua Frieman, Chair of the Department of Astronomy and Astrophysics. Professor Freeman's achievements are really too large to fully describe here, but he spent much of his career at the Fermi Lab Cosmic Physics Center, with which he continues to collaborate, and he co-founded and directed the Dark Energy Survey, a massive international collaboration between 25 institutions in 7 countries that carried out a 6-year survey to map the universe using the largest digital camera ever constructed. He is also an elected member of the National Academy of Sciences and a fellow of the American Academy of Arts and Sciences, among numerous other distinctions. He's here today to talk to us about his career path and how he became a University of Chicago professor. Welcome to the course, Professor Frieman. And how are you doing?
I'm doing well, thanks.
Glad to hear. Can you just please tell our listeners in sort of terms that a layperson will understand, what is your position and what is your subject matter? What do you do at UC?
Sure. So I'm a professor of astronomy and astrophysics at the University of Chicago. I'm also currently chair of the astronomy and astrophysics department, and I do research in cosmology, and I can get into more of that later, but that's my main field of research. And I also teach undergraduate and graduate students, and then do various administrative things as chair of the department.
All right. Yeah, I look forward to hearing more about your current research and your current work. But first, let's go back in time. I'm curious, what did you think you might end up doing when you were young, and did it bear any relationship with what you ended up doing?
Oh, well, I guess it's a question of what you mean by young. When I was, I think my earliest memories of what I wanted to be when I grew up was an astronaut, because I grew up, watching the Apollo moon launches and landings, and was very excited about that. So I think that got me interested in space in general. But I think it really wasn't until I was in college that I figured out that I wanted to pursue cosmology as a calling, as a subject of interest. I think in high school, I had a variety of interests in both humanities and sciences, but there's often this myth about scientists that they all know from age 5. They have some epiphany that gives them some great insight into the universe, like we talk about with Einstein, and that they all knew from then on that that's what they wanted to do. And that certainly wasn't the case with me. It really wasn't until I was halfway through college or more that I, decided on my career path.
Yeah, and I mean, I think especially with somebody who studies the cosmos, it might be tempting to believe that, like, or yeah, I could see there being a moment like that. But I mean, it's interesting. Like, what were your other interests, and maybe when you were in like high school or college age, and how did that sort of coalesce into what you studied now?
Yeah, good question. I think, sort of academically, I think I was always drawn to subjects like history, and then philosophy. And in college, I was kind of trying to decide, what my major would be. I think, my path through college was basically, I would ask all my friends who were the best teachers they had, and I would kind of end up taking classes, not quite, but almost irrespective of what the subject matter was, if there was someone who I had been told was just a fantastic teacher. So my approach to sort of undergraduate education was just try to go to the most inspiring classes. And those ended up being in a variety of fields, from history to literature to linguistics to philosophy. And at some point, I kind of realized, I think, that philosophy was very exciting and interesting, but wasn't necessarily a great career move unless I knew I was going to be an academic philosopher, which I wasn't 100% convinced of. So I think it's, I would say my interests, high school and college, were pretty eclectic. And it really came down to there being a particular lecture I went to as an undergrad that kind of tipped me into cosmology, and in a way made me realize that I could bring together a number of things I was interested in, which was the universe at large, but also this kind of historic perspective, historical, I mentioned interested in history, and I realized or learned that, much of cosmology is trying to reconstruct the past history of the universe.
Mm.
And to me, that was just very compelling. And there was a particular lecture I went to that kind of crystallized all that for me and made me realize I could kind of combine these different interests into one pursuit.
Interesting. So I guess what led you to, decide to sort of take the plunge and pursue a PhD in this field? And I'm especially curious because I understand it was a fairly small field at that time, right?
That's right. So cosmology at that time was much smaller field of research than it is now. It was much more theoretical than it is now. Cosmology is really a mixture of theoretical work and observational or experimental work. But when I was, this was 40 years ago, there was very little data in cosmology, and what data there was quite controversial. But what happened around the time that I was getting interested in the field when I was an undergraduate was this marriage of ideas from the study of elementary particles in physics and the study of cosmology. So it's kind of the smallest scales in the universe and the largest scales of the universe. And what a number of scientists realized at that time was that one would inform the other, that to understand the earliest moments just after the Big Bang, we need to understand how elementary particles behave. And vice versa, if we understood how elementary particles behave, we could predict how the early universe evolved. And moreover, we could use the early universe as a laboratory for understanding the physics of elementary particles. And this was all kind of brought home to me in a lecture by a visiting professor when I was an undergraduate. His name was Dennis Sciama. I think he's particularly famous for being Stephen Hawking's PhD thesis advisor. But he came and gave a lecture which started out, with the present universe. And by the end of the hour, he had gone back to a tiny fraction of a second after the Big Bang. And the notion that you could do this in a coherent way and meaningfully speculate about, the first tiniest fraction of a second after the Big Bang just kind of captured me. And I pretty much knew then and there that that's what I wanted to study. And it also pretty much determined where I would go for graduate school, because there were very few places where people were engaged in that kind of research. And I ended up coming to Chicago because Chicago had two people doing cosmology, and all other universities had 0 or 1 person doing cosmology. And I thought, okay, this must be the center of cosmology because there are two people there. And it turned out it was. And I kind of was able to get in on the ground floor.
Interesting. So, I don't think of the people that I've spoken with, of your colleague, I don't think that anyone else has been part of such a small department like that when they were doing their PhD work. I guess my question is, how was that? But specifically, like, who was there to support you? Who helped you at that stage of your career?
Right. So I came to Chicago to work with Michael Turner and David Schramm, and they were really two people who helped kind of ignite this whole field of the study of the very early universe by combining these notions of particle physics and cosmology. And that was, it's hard to describe, but it was at that period, this is the early 1980s, there was just a tremendous amount of intellectual ferment coalescing around those ideas. But again, it was a very small community of people. And I realized that Chicago was a real center for that kind of activity. And that's what drew me to it. And it was quite an exciting time because David and Michael were really just getting this whole field of research established, but also bringing in, starting to train students. They had a very active group of postdoctoral researchers that they built up. Shortly after I arrived in Chicago, Rocky Cobb arrived at Chicago in Fermi Lab, and he was another critical person in this field in those days. And so there was just this wonderful feeling of kind of being at the center, literally, of the cosmological cosmos.
Yeah.
And being able to watch and participate in all these ideas unfolding.
That sounds very cool. And so I'm curious, could you just take us through sort of, what positions you've held since then? Have you been at the University of Chicago since you started your PhD there?
Well, no. So I was a graduate student, got my PhD at Chicago. I then spent 3 years as a postdoctoral researcher at what's now called the SLAC National Laboratory. It's a Department of Energy laboratory connected with Stanford University, which is where I'd also been an undergraduate. And then at the end of my postdoc, I came back to the Midwest and joined the scientific staff of Fermi Lab, which is another Department of Energy laboratory about an hour west of Chicago that focuses on research in the physics of elementary particles. And so I was, for most of my career, I've been primarily at Fermi Lab, but was also teaching here at the University of Chicago. And then it was only a year and a half ago that I switched over from Fermi Lab to being full-time here at the university. And really, the connection between the University of Chicago and Fermi Lab was a really important one for my career and for this whole field of early universe cosmology. And the synergies between the university and this national lab really helped propel a lot of developments in this field.
Yeah, I mean, could you say more about that? Could you just sort of fill us in on what some of those developments have been?
Sure. Well, I'd say that there's sort of been of two kinds. So one is, as I mentioned, in the early years, cosmology was dominated by theoretical activity, people trying to understand, what's the ultimate theory of elementary particles, what's what we now call a theory of everything, and how could we use cosmology to constrain those theories. And so in the early, late 1980s, at both Fermi Lab and the University of Chicago, we just had a very dynamic group of researchers engaged in those activities. And then subsequently, with technological developments, we started realizing that we could test a lot of these ideas of cosmic evolution by building experiments, building telescopes, observatories, launching telescopes into space. And so increasingly over the subsequent 20 years, cosmology evolved from being primarily a theoretical research activity to being one increasingly driven by data and by the ability to use data to test our ideas about, the first fraction of a second after the Big Bang. And so my research career has kind of evolved from one which was primarily theoretical to one which has become much more experimental, observational. And at both Fermi Lab and Chicago, we kind of engaged in developing observational cosmology as a major subject of research, coming out of the roots we had established in theoretical research. And so now at both Fermi Lab and the university, we have very vibrant departments and research groups engaged in a variety of experiments probing cosmology that really complement the activities of the theorists at both institutions. And examples are, Chicago has been a real center of research in what's called the cosmic microwave background. This is radiation left over from the Big Bang, which is now permeates the universe. It has a temperature just below 3 degrees above absolute zero. And there are patterns of hot and cold spots in this cosmic microwave background, which reveal to us fundamental things about the constituents of the universe and the very early universe, what happened just after the Big Bang. Similarly, we've carried out a series of what we call cosmic surveys. These are making maps of the distribution of galaxies in the universe from millions to now hundreds of millions in order to probe the evolution of the universe, what the universe is made of, and what its earliest moments looked like. And so my research has kind of evolved from these more theoretical beginnings to being much more focused on carrying out and analyzing these cosmic surveys.
Wow. What what an amazing thing for you to be able to not only observe, but to, work with and try to understand these findings as these discoveries as humanity makes them. That's pretty cool.
Yeah, it's been very exciting. And it's I kind of liken it to, I feel like I'm kind of have been living through a renaissance. And I don't know if people in, the 15th century Italy knew that they were living in the Renaissance or not, but certainly in my field has undergone a real renaissance over these last 20 or 30 years, and it's been a real privilege to be part of that.
Yeah. So, what sorts of questions are you asking? What sort of research are you working on these days?
Sure. So I think a kind of a major question of my research really over the last 20 years concerns a subject we call dark energy. So let me just say a little bit about that. So you can ask, what's the universe made of? Well, what do we know exists in the universe? We know that there are atoms. There's things that you and I are made of, that the visible world around us is made of. Everything we see around us is made of atoms. And so you might naturally expect, okay, everything in the universe is fundamentally made of atoms. That turns out to be not the case. In fact, atoms only account for 5% of the total mass or energy that's in the universe. So it's really a minority component of the universe these days. We know that about 25% of the universe is something we call dark matter. We don't know what dark matter is. We think it's made of some kind of elementary particle that has nothing to do with the atoms that we're made of, and that it's the gravity of dark matter which holds galaxies together and is responsible for really the formation of all the structure we see in the universe. But dark matter isn't even the dominant component. We now know from about the last 25 years that the dominant component of the universe is not atoms, it's not dark matter, it's something we call dark energy. The reason we call it dark is because that means it's some substance that doesn't interact with light, doesn't emit light, doesn't absorb light, it doesn't scatter light. So we can't see it with our telescopes, but we know it's there. We infer its existence through its effect on the expansion of the universe itself. So dark matter, we know, is there because it holds galaxies together, and we know that atoms aren't enough to hold galaxies together. Dark energy, we've inferred its existence from the fact that we've known for 100 years that the universe is expanding. All the galaxies we see are moving away from us and from all the other galaxies. And we would have naively expect that as the universe evolves, that expansion would gradually slow down over time because of the gravitational attraction of all the galaxies for all the other galaxies. So even though any galaxy I look at today is moving away from us with a certain speed, previously we would have expected that if I measured that speed tomorrow, it would be slightly less than its speed moving away from me today. Mm-hmm. It turns out that's not the case. Every galaxy we look at, in fact, is speeding up. It's moving away faster at a faster and faster speed over time. That's not what we expected. We expected gravity to slow the expansion of the universe down. So we invented this new substance called dark energy, which has this strange property that it's gravitationally repulsive. Everything else we know about in the universe is gravitationally attractive. If I have any two masses in the universe, they attract each other through the force of gravity. Dark energy has this bizarre property that it makes things gravitationally repel from each other, and that's what can explain that the expansion of the universe is speeding up. So we don't know what dark energy is. We know it's there. We think it's 70% of the universe, so it's the dominant stuff in the universe today. But the only thing we know about it is that it's gravitationally repulsive. We don't know what its other properties are. And so my research has been engaged in making and analyzing these cosmic surveys to try to discover what's the nature of dark energy. What is it really made of? What are its properties? How is it affecting the evolution of the universe?
Wow. One question that we have been asking everyone is, are there further questions that you'd like to pursue as your career goes on? I feel like in this case, it kind of sounds like every time a question is answered in this field, it opens up a literal universe of further questions.
Right. Yeah. So yeah, I would like to know, before I pass on, I would like to know, what the dark energy is. I don't know when we'll figure that out. There's some interesting. It's interesting in fundamental research, and particularly in physics and in cosmology, there are questions we can pose, and we don't know if we'll know the answer, in 3 years or in 300 years or never. And so that sort of, keeps you on your toes. And so I don't know whether dark energy is something that, we'll know much more about in 10 or 20 years, or whether it's going to, take much longer than that to try to figure it out.
Yeah. And what are some aspects of your current job that you don't particularly enjoy? I mean, are there things that you don't care for about this?
Oh, gosh, we don't have enough time for that one. No. I guess I would say, probably like most people, sort of having to deal with bureaucracy, administrative details, all the things that you need to do to keep a department going, a research group going. There are a lot of things that just need to get taken care of, and they're not particularly interesting to do, but they're necessary to do, and they're necessary to do well and in a timely manner. But they're not intrinsically interesting things to spend your time on. And so I would say, it's that set of sort of administrative things that just need to be taken care of, and that are important to take care of, because by taking care of them, I'm enabling other people to not have to spend their time doing it. So it's important, but they're not particularly intrinsically interesting things to do. And my guess is you probably had the same kind of answer from a lot of people. There seems to be an exponential expansion of paperwork, and I think that's partly just the nature of modern institutions, but it's not the fun aspect of the job.
Yes, that is a common refrain I hear. Well, okay, so actually, on that note, I wanted to ask. I saw you wrote that your most recent project started with a conversation between 4 people and ended up being an international project with hundreds of people across, I think, 7 different countries. I would love to just sort of hear your explanation of how a project grows like that, and how you can successfully manage something that's.
Yeah, interesting. Yeah, so the project that I was sort of involved in starting and then growing and then leading was called the Dark Energy Survey. And that was this project to do a big cosmic survey. In order to do that, we needed to put together a large collaboration to build what was then the world's largest digital camera for astronomy, put it on a telescope in Chile, and carried out a survey over 6 years. And clearly, that kind of enterprise requires a lot of people. And it's interesting question, how do these things evolve? Because people have lots of ideas for projects like this. Most of them don't happen. So I can show you lots and lots of papers about we could build this and do that, and they're all great ideas, but very few of them come to fruition. And I think it takes a combination of having initially a core group of people who are really excited about it and whose excitement is infectious, and they convince colleagues that this is so exciting that they have to work on it. And then they convince other colleagues, and kind of, by word of mouth and by going around the world and talking to people, you gradually convince people that this is just really exciting and that they should get on board. That's part of it. And that's really a key part, is sort of building a collaboration of people who want to build a project. And then the second component is convincing some source of funding, usually the federal government, that this is a great idea and that they should give you millions of dollars to build this thing and operate it. And that typically takes years and years to go through various reviews, various proposals, convincing agencies that this is how they should spend their money, convincing universities and laboratory directors to put resources into it. And so there are these multiple stages where these projects can and usually do fail. And what's remarkable to me is that in this case, we were able to put together a very strong collaborative team of people who wanted to build the project, who were then able to convince governments to put in funding for different components of it. We also sort of had the right timing, that the people who operated this telescope wanted an instrument like this, so that it was partly what happens in these cases is you have an alignment of multiple different interests, and if those things align at the same time, then these projects can happen. But it's still a bit of a mystery to me, frankly, how these things really come together, because there's so many ways in which large projects like this can fail, and very few ways in which they can ultimately succeed. Look at the James Webb Space Telescope. It's now, every day you see pictures in the newspaper from JWST. It's fantastic. It's revolutionizing astronomy. But that project cost, $10 billion. And there were a number of times, in its history where it could have, it was in danger of going off the rails and being canceled. And yet there was enough of enough support for it among different communities and funders to keep it going. And it's been tremendous. So I don't know the full recipe for success. I just sort of know what it looks like, but it's in each case, I think it's a bit different how these things really come together. But yes, I have to admit to feeling very odd when going from this room of several of us to our collaboration meetings with 150 people, half of whom I didn't know. And it just was like, okay, how did we get here? I don't, we've been working on this for years, and suddenly we've become this big collaboration carrying out this survey. But it's sort of remarkable to me that the whole thing works.
Yeah. Well, I'm very glad to hear that it did. What of everything that we discussed and everything that you do in your work, what do you find most fulfilling about your role?
Well, I can't limit it to just one, so I'm gonna give you two.
That's fine.
So the one thing, and which is true particularly in the first part of my career, I'd say, is just the kind of the raw thrill of discovery, of finding a new theory, discovering something new in data, realizing that this is potentially has something fundamental to do with the universe. That kind of just joy and thrill of discovery is what really propels me, and I think most of my colleagues, through our careers and keeps us going. So I'd say certainly for the first part of my career, that kind of joy and awe that what I could do actually could have some implications for our understanding of the universe. The second thing, though, has really been mentoring students and postdocs and early career colleagues and enabling them, providing them the resources to do their own research, to make their own discoveries, and realizing that I'm just, increasingly what I'm doing is kind of trying to enable the next generation of scientists to carry on this work. And to see that happening, and to see someone who, maybe started as a struggling student, then eventually succeed and go on to a productive career, that's extremely rewarding as well. So I would really say it's both. It's the joy of discovery and the joy and pride in sort of training a new generation of scholars.
Thank you, Professor Joshua Frieman, for your time today. And course takers, if you enjoyed listening to today's interview, please check out the other ones. Leave us a comment, subscribe, follow, and share this episode with your friends and family. You can find out more about the University of Chicago through uchicago.edu or the university's campus in Hong Kong through uchicago.hk. Stay tuned for more. We'll see you around.